Thank you, Henri, and I'd like to thank the organizers for inviting me. So this is going to be a subset of the 10 authors of the earlier talk, 20% of them. So joint work with Patrick Allen and Jack Thorne. And maybe I'm going to expand the title a bit. Maybe I'll talk about modularity of GL2FP representations over CM fields for P small, and more specifically less than equal to 5. And certainly we don't get such a result in general, but some cases. Okay, so I was going to state the theorem right at the end, but Michael told me he's going to leave halfway, so I'll state the theorem. I'll state the theorem before. Okay, so let me tell you the motivations of this work. So Patrick's talk kind of sets up the context because he, so let K be a CM field like Qi or something. So non-totally real. That is perhaps the interest of the talk. Example. Right, so the motivation of the work is rather than proving potential automorphy of modular curves, you try and prove. So, okay, so the goal maybe, which of course we don't achieve, is to try and get over some obstacles to proving automorphy of elliptic curves rather than potential automorphy. So try automorphy, okay, modularity of elliptic curves over modularity of elliptic curves E over K rather than potential modularity. And in fact, this is not the way we got into this business. I mean, in some sense, we were interested just as an exercise to try and prove some more cases of Sayre's conjecture over totally real fields. So some of the other kind of perhaps goal, which is less interesting to others maybe, but it's kind of my hobby horse, is to try and prove Sayre's conjecture for some more representations over totally real fields. So Sayre's conjecture for projective linear. So Sayre's conjecture over totally real, or analog of course. The analog of Sayre's conjecture over totally real fields. And some of these two themes are related. Over totally real fields, F as opposed to K, right? So for example, representations of the form rho bar of GF into, let's say, the projective group PGL2K. The K is a finite field, totally odd. And rho bar totally odd. Right, for some K small, So I mean, as one there doesn't seem to be any very general result. One could try and as an exercise, try and do it for small k. So for small k. For very small, it's going to be really small. So for example, cardinality of k equal to things like 3, 4. I'm not going to consider 4, 3, 5, 7, 9. We don't 3, 5. You could try and do it for 7, 9. So somehow, so half of these, and often in these cases, there are lots of such results known when you look at GL2K. Right, for example, the result of Ellenberg would be GL2F9. If you have a totally odd representation, then it comes from Hilbert modular form. But although Tate's theorem tells you that such a representation does lift to GL2K bar, it may not lift to GL2K. Right, so somehow you can kind of, so in particular, we were initially interested in proving such a conjecture for rho bar from a totally real field GF into PGL to F5. Let's say, for example, surjective, right? Somehow this case isn't completely known. So it's kind of maybe 1 upon 2 raised to the degree of F over Q cases are known due to work of Taylor. All right. So but anyway, so these were the goals. I'm not going to get there, but so that got us into the problem. And so let me start. After maybe 10-15 minutes, I'll state the main theorem, or at least some sampling of the main theorem. But so let me start by thinking about this first topic, modularity of elliptic curves. I have to go back 20 years to the original strategy of Wiles, to the work of Wiles. So let me recall what Wiles did to set up what is the difficulty in extending Wiles's work to CM fields. Now that we have so many automorphy lifting theorems, right? I mean, what is the obstacle? There's one kind of basic obstacle, which is what we try to overcome. Okay, so modularity of elliptic curves over Q. So the work of the strategy of Wiles is to somehow, So this is like the accidents, various accidents which happen at small primes, right? Somehow that was probably all of you know the story. That you want to prove. So we are given E over Q a semi-stable elliptic curve, and you want to prove its automorphy. So you want to somehow say that LES, the L function of E, comes from a modular form of weight 2 on some gamma naught n, and this is the kind of automorphy we're going to look at rather than some geometric version of it. All right. So how do you, so I mean, so the basic idea was, I mean, this beginning, the sort of, you start by, I mean, Wiles starts by looking at E3, the three torsion of this elliptic curve, right? And you consider the action of GQ. And then you get a representation which is kind of small enough somehow to have some leverage on it. So you get a representation, let me call it, let's say, rho bar E3 from GQ to GL to F3, right? And so this is some kind of double cover of S4. So as a group, this is isomorphic to S4 twiddle. If the projective version is S4, right? So this is one small accident that the group is kind of small, so it's solvable. And the other accident is that this group kind of, because of the representation theory of S4 twiddle, this group literally lifts, not just the Galois representation, but the group lifts to GL to Z root minus 2. Right, so another accident for small primes. So though the kind of image typically is divisible by 3, which might present an obstruction to lifting, but still it lifts. And kind of you look at this. So this, let me call it some, let's say, rho C. Right, so it's a complex representation which lifts the mod 3 representation. And then, for example, when the representation was irreducible, this was kind of a good situation, because there was, as Patrick has already been talking about, there's some kind of automorphy lifting theorem. You can look at the Galois action of GQ on the triadic Tate module of E, and somehow there was this lifting theorem which was proven, which deduced the automorphy of this under suitable conditions, etc., from the automorphy of this modulo 3. Right? So what Wiles did was he showed that by using the theorem of Langlands tunnel, which depends upon the fact that this image is solvable of this rho C, image of rho C is solvable, this so-called octahedral case, which of the Artin conjecture for two-dimensional representations. So Langlands tunnel, what does it tell you? It gives you that rho C arises in the usual fashion from S1 gamma 1, and by the Deligne-Serre construction, it arises from something like this, right? But somehow that was not good enough, because I mean Wiles methods require you to work with kind of Betti cohomology or something of modular curve. So this kind of this was not enough. It had to arise from a cohomological cusp form. So then what he did was you multiply by a kind of Hasse invariant. You multiply by some kind of maybe Eisenstein series of weight 1 or something, congruent to 1 mod 3. Right, and some kind of you realize rho C, not rho C, but rather now this is related, of course, to this is the same as rho E3 bar. So you using this, and then by multiplying, so rho C, the complex representation arises from some form of weight 1, which is not suitable for the method. So you kind of shift the weight to a cohomological weight by multiplying by Eisenstein series congruent to 1 mod 3. Right, so it depends upon multiplication of automorphic forms and having these kind of congruences, Eisenstein series, Hasse invariance available. So from this, you deduce by multiplying by Eisenstein series that rho arises, let's say, from S2 gamma 1 n for some n. Right? And at this point, then the modularity lifting methods could take over in the case. So you first kind of assume in this step maybe that this action is irreducible or something, which in the semi-stable case implies it's better than irreducible. It's not in these bad dihedral cases. And so then it arises from S2 gamma 1 n, and there's automorphy lifting theorems or modularity lifting theorems, then deduced that the triadic Tate module came from a new form. Right, so that was the first step of the method. Now the second step was this. So this is in some sense the step we want to focus on. How do you do this over CM fields? And the second thing also which figures in our work is this 3-5 switching, which happens in Wiles' work. So in the case when so the other step in the to get over, so it may be that E3 is reducible. If E3 reducible, Right, then what do you do? So then Wiles kind of constructed another elliptic curve. So you looked at E5. Right, of course, all this is a well-known story. Anyway, so you look at E5. This also has the action of GQ. Then if this were reducible and kind of this, it implies that E5 is irreducible as a GQ module, right? Because of curve x0, I mean, at least you can assume perhaps, or if you are semi-stable, that's literally true. Because x0, 15 is a curve, I think, of genus 1. It has few rational points, perhaps nothing which intervenes in the proof. And so now this is irreducible, and so then you can somehow look at this rho bar E5 representation, which this gives rise to, right? And we call it, let's say, rho bar. Okay, rho bar. And you look at this kind of moduli space, so which classifies this twists of elliptic curves with this rho bar 5 structure, right? And this turns out to be a curve just P1. It is genus 0 with a rational point coming from E. And then from here, using some Hilbert irreducibility type argument, you can construct from the fact that, so this is just P1. You can construct by Hilbert irreducibility or various something else. You can construct another elliptic curve semi-stable. There exists semi-stable E primed over Q. Right, which realizes this 5 torsion, but mod 3 now it is good, right? So somehow, so that rho bar E primed 5 is the same as rho bar E5, right? And at 3 it's become good, and rho bar. E prime 3 is irreducible. Right, and then you play this game that, okay, as as E prime is this curve with a robust, with a big with a sort of the rho prime rho bar, the mod 3 representation is irreducible. Again, modularity lifting that tells you that E prime is modular, hence rho bar E prime 5 is modular, which is the same as rho bar E5, and then you apply modularity lifting to the 5 adictate module perhaps of E or something. Right, so this was the rough shape of the proof. So if you want to imitate this proof for let's say Qi, so how would you start? I mean, suppose you want to imitate this proof for Qi. Right, any questions? Yeah. So you want to follow the same paradigm and start with an elliptic curve over a CM field, let's say Qi, and try to play the same game. Right, so how do you imitate? Try and imitate this strategy. Imitate Wiles strategy over CM fields. Let's say Qi. Right, you can try to do the same thing. So you start with the elliptic curve E over Qi, and then again, I mean, you can look at the mod 3 representation again. So you look at you consider from this rho bar E3. I'm just going to call this K because you can look at this representation from rho bar Ek from Gk to Gl to F mod, Z mod 3. Right, and again, I mean, the group theory works, so you can certainly lift this to a GL2 complex, I mean, to a complex representation. Right, so you can lift this to a complex representation, and you can apply Langlands tunnel here. Right, you can apply Langlands tunnel to rho C. So let me, I'm going to look at the. Okay. So apply Langlands tunnel to rho C. Langlands tunnel is a very general theorem. It works over all number fields. So apply Langlands tunnel again here. So now you just get that rho C now comes from some kind of form. So it arises from. So therefore this arises in some sense it arises in the usual way from some, so maybe let's say some form pi in the cuspidal automorphic representation of GL2 of, right? So there's no problem there. But now the problem is that for the automorphy lifting theorem, which Patrick was talking about, for that to for those to work, you somehow need to realize it as coming from the cohomology of some congruent subgroup of SL2. Okay. But on the other hand, there's no the second step of multiplication by the Hasse invariant. There's no analog. So on the other hand, there's at least not that I know of. No, but problem pi is not cohomological. Pi need not pi. We don't know. So pi is of kind of a Galois type. It's some Artin type. It's certainly there's no known cohomological interpretation of it. So we don't know how to produce, how to show from this, how to use this to show that the original representation you're interested in. So maybe I should have called this rho bar E3 or something. To show that rho bar E3 arises from some cohomological form. Right, so somehow that's the issue, which is basically what we are dealing with. We do not know how to do this. I mean, I think I've asked around, and the experts have told me that there's no obvious way of using some fancy functoriality or something and getting this in somehow. All right. So somehow you have to do this for yourself. You have to do it by hand. There's nothing you can appeal to maybe. Okay. So what is the strategy? We can try to follow whiles and look at the 3-5 switch, but again that doesn't work. So try some, okay, so now this is problematic. You don't know how to somehow show that it comes from a place where you can start to apply automorphy lifting. You would be maybe even happier if it probably came from H star, some cohomology with F3 coefficients of some congruent subgroup. But there's no way of kind of somehow doing this, apparently. Okay. So what do you do? So you can try the 3-5 switch. So to go to the second step of whiles and try the 3-5 switch. Right, so okay, so your mod 3 representation is problematic. You can't work with it. So you start with that same E. I'm not dealing with this issue of reducibility and so on. Okay, but so now you can still try and switch so that you can change to a mod 3 representation which is cohomological. Right. So the idea you could try, what you could do is you could look at E5, right, and assume it's irreducible and all that. That's not the issue. So you kind of look at rho bar E5 from GK to GL2 of Z mod 5, right? So this assume it's kind of irreducible, determinant characteristic, it will be cyclotomic, etc. And now you look at the twisted moduli space for this representation, right? And now in this space you try to find an elliptica whose 3 torsion somehow has a cohomological lift, whose 3 torsion arises from a cohomological cusp form. Or more precisely, what you can do is you can sort of fix. So you need a supply of mod 3 representations which are cohomological. Now one way of doing this is to start from a representation over the totally real subfield of K plus. So you have this structure K plus, totally, so K plus is my notation for the totally real subfield of a CM field. Right, so the idea is now to try and pivot on 5 and try to kind of locate another elliptica of E prime which has this 5 torsion in common with the elliptica we are interested in. But the mod 3 torsion is suitable, it's cohomological, admits a cohomological lift. So you can try and do that, but for that you need a supply. You need a supply of cohomological representations at 3. So what is the supply? A supply is that you can start from representation of K plus and base change, right? Base change is available. So you can start with for example, in Qi, this is just Q. So you can in the second step. So somehow in this modular space, which is again isomorphic to P1, you want to locate a point whose mod 3 torsion is suitable for application of the method. So in particular, it arises from a cohomological cusp form. Now you can try to impose a mod 3 level structure which somehow by construction admits a cohomological lift, and a supply of such representations comes from base changing things coming from elliptic modular forms from Q to K or K plus to K. Right. So, for example, you can look at a thing which arises from, let's say, a cusp form you can fix some representation or auxiliary representation which kind of is cohomological, and then so this gives rise to some rho bar 3 structure. Let me call this rho bar 5. And you can look at this augmented moduli space. You can fix the twist of x15. So you can look at rho bar 5 and rho bar 3. Right, rho bar 3. This is like rho bar 3. I'm going to call this rho f bar restricted to gk or something. Right, so somehow you fix a cohomological mod 3 representation, and you want a good supply of these. Maybe in the end it will prove to be vital that you just don't fix some random. You don't make your choices too soon. You allow yourself a certain latitude amongst a good supply. All right. So now this is some twist of x15. There's a curve of some genus. Maybe it's 3 or something. I don't know. It's a curve of frighteningly large genus. Okay. So on the other hand, it kind of admits a map. It's a solvable cover of something nice, right? It's a solvable cover of x rho bar 5. Maybe something like PGL to F3 S4, some S4 type cover. Right. So now you would think that you should win because somehow there's also in the background there's solvable descent. You'd win that if you could do this kind of thing, realizing this mod 5 and mod 3 representations in a common elliptic curve over a solvable extension of or solvable CM extension though. So the trouble is that would win if we could show that at least we had a starting point. If we could show that this guy was non-empty for some L over K solvable CM extension. Right? Because then somehow you could prove the modularity of this you would find an elliptical L which some E prime or something over L which by consulting its mod 3 representation you would know it's modular, and then you could look at the representation coming from E and then kind of the usual solvable descent argument, right? So somehow it would be enough to find solvable points on this twisted curve, and it looks promising where it's a solvable cover of P1, but this is impossible to do. Somehow what is easy is what is possible. Possible. It's easy to find solvable points. Easy to find it's either easy to find CM points, and it's also easy to find solvable points, but the conjunction looks hard. So one can do either of them, but to do both, so easy to do either CM points but not both. But it's hard to do both. Hard to achieve both. CM extent, sorry. CM, CM in my sense, okay. No, not in yours, but hard to achieve. So hard to achieve this, right? So somehow this trick doesn't really work, but it somehow gives you something that you should be trying to do some geometry which uses the fact that PGL to F3 is solvable. So rather than using some kind of more difficult theorems of Langlands tunnel which rely upon the solvability but more in indirect ways, you can really try and literally use the fact that PGLs, that small groups, these PGL to FPs for small p are solvable. Right? So you can try and begin to exploit that. Okay, anyway, so this doesn't work. So it doesn't work. All right. So now as a last resort, the only thing you can do is look at p equal to 2. P equal to 2 has to be gone to only under dire circumstances. Okay, so p equal to 2 is so what we try then is a 2-3 switch. So I wanted to point out that maybe this question is very hard. In something, even if you look at some very baby version of this, it looks impossible. So for example, if you look at, so this is just a curiosity. It's not very. So for example, an easier thing would be you look at y, some hyperelliptical. You can look at y squared equal to fx. Well, let's say f is in kx. Then the challenge is to find points of this over CM quadratic extensions of K. Looks impossible, looks very hard. Try and find, or even you could all solvable, we could have solvable, but okay. But to try to use the structure of this degree 2 mapping, you could try and find solvable points of this, whatever this is. So trying and find solvable CM points, again in my sense. Try and find, okay, not to try and find L over K CM quadratic. Such that C of L is non-zero, or if there's, yeah, or something like that. I mean, it seems hard. I mean, it's hard to do any somehow kind of trying to feed into some Diophantine problem. The fact that it's CM, it's to achieving CM seems very hard. Though there is a small case of this problem which we solve and which is important for us later. Maybe the way I've written it, okay, but anyway, you can get the drift. All right. So therefore, what you try to do is a 2-3 switch. Okay, so I didn't succeed in stating the theorem before Michael went away. So now I won't state it till the end. All right. All right. So now you can try a 3-2-3 switch. Right here, what would be the idea? Someone look at the mod 2 representation and try to apply. Okay, so consider, for example, the same thing. You have E over K, some CM field, and you consider rho bar E2 from GK to GL2 Z mod 2. Now, this group is very innocuous. It is isomorphic to SL2, or this is S3, right? So, this is a kind of a dihedral representation. This representation is induced from some quadratic extension, need not be CM, so induced from some character chi, right? So it's induced from some character chi L over K quadratic, and chi is a character. Now here getting a cohomological lift is easy, right? You can just kind of induce, you can just change the infinity type of chi and make it congruent, still congruent to chi mod 2. So you're here getting a cohomological, some kind of cohomological lift is easy. Okay, you can get plenty of cohomological lifts by doing the obvious thing, which is get cohomological lifts. Hecker and so on, theta series. So you can look at things of the form where you kind of make chi congruent to a character chi prime mod 2, and kind of chi prime just kind of has as a sufficiently suitable infinity type, but somehow it's not useful, right? Because now comes the constraint that when one uses automorphy lifting theorems, one is often treading a very narrow path. So I mean, you have to fit your theorems, you have to fit your what you have to what you can prove in automorphy lifting. So the kind of automorphy lifting one can actually prove is that in this case, as Patrick had done earlier, Patrick had done this kind of stuff of automorphy lifting for residually dihedral representations over totally real fields, right? And his strategy relied upon the work of Skinner-Wiles. So where they don't prove an R equal to T, somehow that's too small, they work in a bigger space of R ordinary equal to T ordinary, some big space, right? And there's some kind of connectivity argument. But so without going into too much, we have probably seen a lot of automorphy lifting today, so I'm going to stay away from any details about automorphy lifting. So I'll just tell you the general strategy, which then helps us reduce to a situation where we think we can prove an automorphy lifting. So so this looks good because you have a mod 2 representation. Let's assume it's irreducible, etc. That's not a major issue for us. And it has a cohomological lift, but somehow this cohomological lift is of no use because it's somehow we want to prove an ordinary modularity lifting theorem, and somehow this lift is not going to be in the situations we want to which are kind of workable for us. This lift is not going to be ordinary. All right, so you have a cohomological lift, but the problem is you do not have an ordinary cohomological lift in the situation where we can actually hope to prove something. All right, so here the automorphy lifting theorem here is kind of inspired by Skinner-Wiles, this kind of beautiful argument of connectivity argument of use that idea to do the dihedral case for totally real fields. So this they did the somehow reducible case, residually reducible case, and in fact the dihedral case is done by. Alright, so some of the idea is that you try to prove an R odd equal to T odd kind of theorem, right? So somehow you don't work with fixed weights but variable weights, but in the ordinary setting. So there's also T odd, and then you kind of have this kind of look at the spec of R and look at its connected components, right? And then T odd also has its own connected components. And the idea is to kind of locate on the connectivity argument is you try to prove component by component that all points of the given component are modular by identifying it in some sense with the corresponding component here. And for that you need to have nice primes. Okay, I'm not going to get into all that. So you have these kind of nice primes which you have to locate somehow. And then once you have a nice prime, once you find one point on this which is automorphic and it's sufficiently good, for example, it's away from, it's not dihedral, then you can somehow prove a automorphy lifting theorem which then fills out the automorphy of this entire component, right? But for that, somehow the bad locus is because somehow the Taylor-Wiles method does not work. The cohomology killing primes do not exist in the p equal to 2 case when the residual representation is dihedral. So somehow, or whenever you're confronted with a dihedral representation. So you have to stay away from the dihedral locus. So here in, okay, so this is two different worlds which are then R equal to T is a way of going from one to the other. So sitting inside here, okay, there's some dihedral locus. So of course we have a residually dihedral representation and we have a dihedral locus. And if this dihedral locus is, for example, is a component of this ring, it's of the same dimension as the ambient ring, then you're in trouble because you have to somehow stay away from the dihedral locus. So the problem here is to avoid the situation of the dihedral lifts being too numerous, you have to impose on the condition on the inducing data that it's not ordinary, right? So somehow, I mean, so this is purely, so all this stuff comes from the automorphy lifting theorem one can prove. So here the trouble is that this is cohomological, lots of cohomological lifts, but none of them can be ordinary in the situation where, so want dihedral locus to be small for this automorphy lifting theorem. So this is again so the same thing which showed up in Patrick's thesis. So want dihedral locus to be small. So for that somehow tells you, and it's ordinary and so on. So want that inducing data. So thus, so want, which implies that want that this quadratic extension in this situation, the K is a CM field. The only kind of thing which will allow you to inhibit the existence of dihedral lifts is if some local behavior is not correct at 2. So want that L over K is not split at all primes about 2. Well, if it was split at all primes above 2, these kind of dihedral lifts which are exactly of these form, somehow they'll be too numerous. The Skinner-Wiles method doesn't work. And on the other hand, once you assume it's not split at all V dividing 2, this kind of induced lift is no longer ordinary, right? So you're kind of caught in this trouble.
Do you mean there is A prime above 2 where it's
yeah, for example.
non-split at every point?
A prime also would be, but we okay. As you see, we'll assume more. One that L over K is not split at all V dividing 2. Then this implies that these induced lifts are never ordinary. I mean, these cohomological lifts are not ordinary. Though the weight 1 kind of lifting is ordinary, but the R10 lift is ordinary. You know, but ind chi twiddle L over K. Cohomological, but not ordinary. Right, so you're in a bind, kind of somehow in the way you carry. So you've gone to mod 2 because you thought you kind of had something going because the mod 2 representation was small and you could kind of construct cohomological lists for free, but they are not useful for the method. Right, so what you do instead is, of course, what you do instead is that you kind of construct, you play this 2-3 switch where you fix the mod 3 representation and try to realize fix another auxiliary mod 2 representation which is induced from something which is not split at all primes about 2, right? So that's kind of the idea. Okay, so what do you do? So okay, so I've explained why kind of the automorphy lifting theorems which are available do not allow us to work with situations in which there are obvious cohomological ordinary lifts. So we have to do something. We have to again we have to revert back to the idea of trying to work over k plus and then base change to k. Right? So some of these mod 2 representations we construct. Okay, so let me now. I tend not to have theorems in my talk, so let me just say that automorphy lifting theorem we prove. Right, so some of the two-adic automorphy lifting theorem, which tells us what kind of mod 2 representation we should be looking for which it is possible to prove automorphy lifting. So the idea is going to be you want to show, you start with this mod 3 representation, 5 has failed you look at 2, 2 is failing you, but then now you kind of rig up the mod 2 representation so that it comes from below, from k plus, and it's non-ordinary in the sense that its inducing data is not ordinary, by which I mean not all primes above 2 split, and then try to work from there. Okay, so let me say this theorem. This is in some sense the main theorem of this paper. So this is the main kind of two-adic automorphy lifting theorem. This is joint work with Patrick and Jack. Okay, so what is the theorem? So let K be a CM field. So I want to state this theorem to tell you what kind of mod 2 representations I should be trying to realize in the common wave and mod 3 and mod 2 from an elliptical. So let K be a CM field and rho a geometric two-adic representation, rho from GK to GL to Q2 bar. Continuous sort of standard, I mean a geometric representation such that one rho bar is generic as explained in Patrick's talk. So it's some local assumption in some sense a local assumption as Patrick explained to me over the Galois closure of K, right, of rho bar base change of rho bar. Yeah. So rho bar is this rho gives rise to rho bar. So rho bar is generic in what you say, some local assumption. So rho bar is absolutely irreducible of solvable image. So basically in the p equal to 2 cases, if it's irreducible, then all the other solvable cases go out. The only thing which remains is dihedral. So rho bar is absolutely irreducible of solvable image. So basically dihedral. And therefore it's and we assume it's of the form. Now comes the key assumption. So now rho bar therefore is of the form in K over L over K of chi, right? And you assume that this representation descends to K plus. So this is a condition on the residual representation. Rho bar extends, and of course it has to extend to a dihedral representation. Right, so K plus, I recall, is the totally real subfield of K. Okay, so it extends to K plus. So somehow that is used to produce cohomological ordinary liftings in spite of the data of the inducing data not being ordinary. And 3 is this local condition which forbids it from the data being ordinary, but we have a little more. Okay, so maybe this should be part of, okay. And we assume that for all v dividing 2 on k, places of k, and the local extension, so LW is equal to kv square root of beta, where this is like this Tre Ramiffi in the sense of Serre. Okay, so the kv root beta, where beta is some element of odd valuation at 2. Right, so this is beta v or something. So this local complete, so we are assuming for v, so we are looking at v, and there's a unique place, it's a ramified, we are assuming it's going to be a ramified extension for each local place dividing 2, and that ramified extension is given of the form kv root beta v, so that the order or something of beta v is odd. Right? So this is the Tre Ramiffi in some sense. In fact, maybe perhaps this beta v isn't K plus. Okay, anyway. Okay, so that's kind of this condition that the inducing data is not ordinary. Of course, the rho bar in some sense is ordinary, but the inducing data is not ordinary, and And now okay, so now these are all the assumptions on the residual representation, and of course then for we assume that rho is rho for each place dividing 2 is ordinary of weight 0 at 2. Weight 0 in the sense of weight 2 at 2 is ordinary. Right, so basically it looks like on inertia it looks like maybe some cyclotomic character stuff. Right, so under this condition you deduce that so geometric by that of course I mean unramified outside finitely many primes, and then it's Hodge state we have ordinary and Hodge state at places above 2, and the weights are 1 and 0. Right, in that situation we prove the conclusion is, so these are all the assumptions, and then the conclusion is then rho is automorphic. Then rho, so okay, so then the conclusion is then rho arises from a, I want to specify, arises from a cohomological cusp form, ordinary. Right. So okay, so this is the automorphy lifting theorem which we prove, and in some sense the main theorem of the paper. But now to make the application to the elliptic curve, somehow now you have to cook up a situation where you can apply this modularity lifting theorem in the situation where you're given an elliptic curve, it has a mod 3 representation. You do not know how to prove it's cohomological. You're going to choose a mod 2 representation which comes and from trying to satisfy the requirements of this theorem, and then try to find a common elliptic curve which realizes the mod 3 and mod 2 representation. Right? So that's the basic idea. And okay, so you try and do that. So very roughly, so I'm kind of running out of time, but okay, so what is, in some sense there's some pretty Diophantine argument here which I'll kind of tell you about. So somehow you're going to start with the elliptic curve where you have no choice. That gives you a mod 3 representation, you have not much choice. But now you're going to change the elliptic curve. You're going to the mod 2 representation may not be of the form you want, so you have to discard E, and you have to try and find, you have to fix another auxiliary mod 2 representation and try to find an elliptic curve which fits the given mod 3 representation and an auxiliary mod 2 representation which is adapted to the hypothesis of the theorem. Right, so somehow that's what you want to do. Okay, so basically we need a way of, given a mod 2 representation and a mod 3 representation, let's say both irreducible with cyclotomic determinant character, we need a criterion for how to realize it in a common elliptic curve. Right, so this is the so-called 2-3 switch. Okay, so somehow so the 2-3 switch now is, you're given an elliptic curve K which you want to prove modular, so in the sense of LES is equal to L pi S for some cohomological cusp form, for some form in GL2AK, and you want to prove it's modular, so you look at E3, but then its E2 may be not very good, so you kind of, so this is going to give you the mod 3 representation, assume it's irreducible. And then now, so I want to find, construct an auxiliary mod 2 consider auxiliary mod 2 representation. From let's say rho bar 2 or something, I don't know, GK plus, let's say, to GL2 SL2 F2 irreducible or something. So somehow so that it satisfies the data of this theorem, so that rho 2, so that the inducing data is not ordinary. Right, and then the idea is, of course, to find an elliptic curve which realizes mod 3 and mod 2 representation, and then try to apply the automorphy lifting theorem as stated to the twoadic representation coming from the E, and then hence all that stuff. Okay. So, but how do you do this? I mean, how do you cook up, how do you patch together a mod 2 and a mod 3 representation? You need to do something. So the general problem you might try to address is you're given two elliptic curves, and you look at a mod 2 representation coming from one of them, a mod 3 representation coming from the other. How do you interpolate it into a common elliptic curve, right? So that's the general situation you might try to look at. Okay, I'm going to just tell you the basic idea. So rather than trying to ensure all the hypotheses we need to apply these automorphic lifting. So as I said, the main thing is to kind of ensure this global descent. I mean, you're working with K, but you want this representation to come from K plus. All the local other properties are not so hard to get by usual traditional arguments. You can get them, but to get this kind of global descent on the mod 2 representation and still make it come from an elliptical seems nice. So it seems to require arguments which are newer. Okay, so the general sort of situation is. The general situation is you're given a. So the general situation. So the general problem maybe. So you're given. Let's say you're given two elliptic curves A and E over K. Right. So suppose you're given two elliptic curves over K. Now you look at the mod 2 representation arising from this. And the mod 3 representation arising from it, of course, in general, unequal. Okay, so A2 and E3. Right, both are going to be, let's say they're irreducible and they're going to have cyclotomic determinant. So the question is, when does there exist an elliptic curve which realizes this mod 2 and mod 3 representation? So when is there an elliptic curve, let's say F over E, F over K rather, F over K, such that F2 is isomorphic to A2 as GK modules, and F3 is isomorphic to E3. Right, so the answer is not always. There's an obstruction. There's an obstruction coming from the discriminants of these. Of course, discriminant is not a well-defined concept, but a modulo 12th power as it is. So there's an obstruction coming from discriminants. So there's a necessary condition which has to be satisfied. Because if you can imagine a common elliptic curve realizing this, somehow you'll see that, for example, this will be the splitting field of y squared equal to cubic polynomial. It will contain the square root of the discriminant. Right, so and this will also contain, in some sense, the splitting field of this will be related to cube root of the discriminant. So because of this, there's a kind of constraint. So the proposition is so the answer is not always, and the necessary condition is somehow that if you look at the discriminant of delta A, this should be congruent to the discriminant of delta E. So there's a discriminant modulo, let's say K star to the 6th or something. Right, so from this you get its modulo K star squared, and from this you get its modulo K star cubed. So commonly, I mean, together. Okay, so the proposition is that this is a necessary, sufficient condition. So the proposition is this is sufficient. Delta, assume delta A is congruent to delta E modulo. Then there exists an elliptic curve, etc. Such that. Right, so somehow this is the kind of Diophantine result you need to kind of to play this game. You need to you have this kind of theorem which tells you that you will be done if you could satisfy these constraints of discriminants, right? So on the other hand, how do you do this? I mean, what you're going to do, of course, I'm not going to I'll kind of be brief. I mean, you're going to start with an elliptic curve maybe which comes from K plus and look at its two torsion, and you cook up various other conditions, and then you start with you kind of you realize your mod 3 representation as coming from an elliptic curve, which is easy, it's well known. You can do that, and now you're going to give these two representations, and you're going to but then on the other hand, this constraint has to be satisfied, right? To to make them come from a common elliptical. So you have to kind of ensure that is satisfied, and for that you need this kind of nice lemma in Kummer theory. As I said, I mean, somehow to do Diophantine geometry over CM field is very hard. To produce CM points with some solvable data and so on is very hard. But there's one situation in which some basic algebraic number theory gives you some hold, which is the following proposition. So how are you going to try and do this? So there's somehow you need some kind of element, some lemma. We need a criterion for a Kummer extension of a CM field to be CM, right? So here's the lemma that let K be a CM field. Let's say imaginary CM field. I don't know. So this is one situation in kind of extracting roots and trying to do kind of geometry where you produce points of such things over solvable extensions, solvable CM extensions. Okay, so K imaginary CM field and n an integer. And A in, let's say A in K star. Then the splitting field of the Kummer extension, nth root of A, then the splitting field of x to the n minus A is a CM extension. Is a CM, and of course it's solvable. The question is whether when is it a CM extension? Is a CM solvable extension? So in fact, the lemma in this form was proven by Najmuddin, Fakhruddin. Then the splitting field of x is a CM solvable extension if and only if you look at the norm from K to K plus of A, this should be equal to the nth power of a totally positive element of K plus is equal to B to the n for B a totally positive element of K plus. In fact, we need this in the special case when the norm is just 1. There's a more direct proof. This proof is a little longer. Okay, so now once you do this, so now you have some kind of criterion for when is a CM, when is a Kummer extension CM. When is a Kummer extension CM? And now somehow you can imagine that trying to satisfy this condition that two discriminants are equal modulo, some powers can be done then by a solvable Kummer extension. Okay, so the upshot is now that I'm running out of time. I'll kind of the upshot is that you can somehow achieve this business of trying to find, given a mod 3 representation, to find an auxiliary mod 2 representation after CM solvable base change, so that you can find a common elliptic curve which realizes the mod 3 and mod 2 representation, etc. Right? So somehow I've given you the ingredients. Now you have to cook them and get this thing. Okay. So and then so now I'll end with a theorem. Okay. So let me just state one illustrative theorem. So for example, perhaps some of this can be optimized. Of course, it's limited by the automorphy lifting theorem, not only at p equal to 2, but at other primes 3 and 5, for example, where we are forced to use ordinary lifting theorems because of what is known. Okay, so for example, let me prove a mod 3 theorem. So okay, so fine. So putting all this together, you get a theorem which in some sense at least begins to overcome the difficulty in the while strategy, the first step. Okay, so let K be a CM field. And then you have a technical assumption such that zeta 5 is not in K with cyclotomic and rho bar from GK to GL to F3 representation with cyclotomic determinant character. Suppose for now you have some kind of funny assumption. Suppose for V dividing 5, so because we also play some 3-5 trick and so on. Suppose for V dividing 5, rho bar, basically the assumption is that rho bar restricted to GKV. That's what I'm going to. Arises from a Tate elliptic curve at K. So maybe it's of the form, something of the form up to sine or something of the forms. Right. Rho bar is a then rho bar arises from a modular elliptic curve. Over K. Yes, so in some sense, it gets around the fact that we do not have Langlands tunnel to, and of course, this is it's modular, it's coming an elliptic curve, so it's kind of cohomological. You get a cohomological lift. And okay, maybe as I've run out of time, I'll stop. Thank you.